Okay, welcome everybody. Today we're going to have a look at the electron configuration filling order. So in the past we've been studying how electrons organize themselves in electron shells around the nucleus. So we did look at how to write the electron configuration using something called Bohr's model. Now Bohr saw the atom existing in more of this kind of two-dimensional manner, in which you've got a core nucleus here in the center, and then around that core nucleus there are electron shells, and these electrons here just sort of orbit around the nucleus. So kind of saw it as like maybe kind of the sun being here and all the electrons being like the little planets that are rotating around the sun, and they must stay within these energy levels. Okay, but it's more or less a two-dimensional way of viewing the atom. Now we also had a look at how you would write the electron configuration using Bohr's model, and that was just like counting the amount of electrons in the first shell. So in this case it would be 2, then the next shell, which is 8, final shell is 4. So that's how you would write the electron configuration. Now, it turns out that Bohr's model is inaccurate. It's very simplistic. It's not actually how scientists view the atom today. So scientists have, due to the discovery of quantum physics, this is kind of what an atom looks like. Now, please don't freak out. You're not going to have to draw these orbitals, they're called. Basically, this is Schrodinger's model, and it is a quantum model. And it looks at the atom in terms of specifically the electron shells around in an atom as three-dimensional spaces in which electrons exist. So you can see here there's the core nucleus in the center there, and you can see that there's this space here. It's actually a three-dimensional space, and it's a sphere, right? So this is called the 1s orbital. Okay, and then there's another sphere around this smaller sphere. Now this is called a 2s orbital. Okay, so what electrons actually do, each orbital is actually only capable of holding 2 electrons. Okay, so within that 1s orbital you would have 2 electrons within that space, so they can present themselves anywhere within that space. They can't really get out of that space, but you also can't predict where they're going to be, because they're actually popping in and out of reality all the time. So that's what quantum physics says. Okay, then we have the 2s orbital. Again, it's a bit larger, and again only 2 electrons can fit into that. And then we have the 2p orbitals. Now these orbitals, you can see, are a different geometry. You can see, and again in each one of these orbitals here, there's sort of you can see that there's 6 different blobs. They are actually, so one electron would probably go in one of these orbitals here, and then another electron into this. Then so that's 2 electrons into one orbital, and then again 1 electron here, 1 electron there, say, and then 1 electron here, 1 electron there. So it's these two models. I guess the Schrodinger's model of looking at how electrons are organized in an atom is just is more specific, because it says, okay, well, within this within the second, this is the second shell of the Bohr's model. So within the second shell actually doesn't really look just like this. It's not just 8 electrons being organized in this like lovely little electron shell here. It's actually more complicated than that. Those 8 electrons in the Schrodinger's model are actually, I just showed you that how the 2p orbital is filled, there was also a 2s orbital, which is this sphere here. So I'll put one electron in there and then another electron in there just to sort of show you. And you can see that if you count everything that's going on in the sort of the second shell, there's still 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons are still being filled in the second shell. I mean, that hasn't changed. It's just that within that shell there are specific geometries, spaces that contain the electrons. And that's just, so the Schrodinger's model is just looking at how those electron shells are organized, what their geometry is like, because they're not just a circle like this, like shown in the Bohr's model. They actually have a particular category. Okay, so Schrodinger's model is just a more specific, categorized way of looking at how electrons fill in space around the atom, and it has very important implications in quantum physics, which you do not have to worry about when you're doing chemistry in year 11 and 12. So don't worry about that. But it is important to appreciate that the Bohr's model is actually an outdated model. The Schrodinger's model is actually how an atom really looks like. Okay, so what you're studying sometimes is outdated. So don't be surprised when there's something a lot more complicated out there. Now, it turns out that also the periodic table is does help us with does organize things into subshells as well. So I did mention that there are things called well, orbitals and then subshells. Now I will make this a little bit more clear in a moment, but basically we did look at how when we go from left to right across a period that more and more electrons fill in into that atom. So if we take, for example, I don't know, fluorine, and just use the Bohr's model to draw out fluorine. So fluorine's right here, and it has 1, 2 electron shells around it, so I'm going to draw them in using Bohr's model. I'm not going to draw that complicated looking Schrodinger's model, okay? Just for simplification, of course. So the first shell contains 2 electrons, 1, 2. Okay, so this is the first shell. Now, in Schrodinger's model, that first period here is referred to as 1s. 1s. And now the reason it's 1s is S stands for spherical, and I did show you just a moment ago how the sphere looks like around an atom, the 1s subshell. You can see here it's this little geometric sphere in the center there, okay, around the nucleus. So in that 1s orbital, that's actually a 3D sphere. You would have and electrons are sometimes drawn like this, going up and pointing down, and basically that's because one electron, electrons have directions. This gets really complicated in quantum physics and chemistry at university, but basically it just shows that they have to be opposing each other. Okay, so there has to be one electron pointing up and one electron pointing down in a orbital. Otherwise, if they're both pointing up or if they're both pointing down, it's actually going to cause repulsion between electrons. Okay, so that's the 1s orbital. And coming back to the periodic table, the 1s orbital is the hydrogen and the helium. So a lot of the time to show this, we actually write 1s. So the first shell is spherical, okay, and it has a maximum of 2 electrons that can go into it. And that's what we see in fluorine. In fluorine, we see that 2 electrons are occupying the very first shell. So this little 2 up here is actually telling you how many electrons. This here is telling you, the S is telling you the subshell, and the 1 out the front is actually telling you which electron shell it is. Because we need to know whether, we're filling up the first shell or whether we're filling up, I don't know, the 5th one or something. Okay, so this is the order so far. So in fluorine, we know that in the first, if we wrote this with the Bohr's model, we'll just write 2, comma. Okay, but this is now, we also have to understand the electron configuration filling order. So in the first shell, there are the spherical shell, we have 2 electrons. So we're essentially, Bohr's model is just looking at the top part, just the electrons, but we know better than that. We know that there's some kind of organization of these specific electrons in spheres, in shells, okay, in geometric structures. Okay, let's keep going. Now, and I should really use a highlighter. Sorry for those of you that may be a bit OCD. So the next is the second shell. Now in Bohr's model, we know we'll just go like, okay, 1, 2. I'm going to change color. I'll explain why in a second. So 1, 2, and then 3, 4, 5, 6, 7. Okay, so I'm going to draw these out. So 1, 2, 3, 4, 5, 6, 7. Okay, so Bohr's model would say, okay, well, there's 2 electrons in the first shell and there's 7 in the last shell of fluorine. And that would be it for the Bohr's model. But we actually know that there's a more specific way of categorizing those electrons in the second shell. I'll show you back, let's go back to the example that we saw before. So we saw that there's something called a 2s orbital, and then there are, interestingly, 2p orbitals. Now the 2s orbital, I'll try to draw this in a different color, might use red. The 2s orbitals, that is this sphere right here. Okay, and so again, because you've got this is a spherical orbital, and all you can have in a spherical orbital are 2 electrons, one pointing up and the other one pointing down. That's really hard to see. I hope you can see that. But again, there are only 2 electrons possible in that spherical orbital. Now that's actually shown in the periodic table. That 2s orbital is actually acknowledged in the periodic table, surprisingly. And you can see that the 2 yellow colored highlights that I made, this is actually the filling order of the s orbital. So the spherical orbital. So you can see that to get up to fluorine, you first have to, in the second shell, you'll first have a spherical orbital to fill, and then guess what? The blue one indicates the other subshell, the p subshell. Okay, so if we look back at our atom here, we can see that we have the 2p orbital. And so what ends up happening in fluorine's case, and I will try to clean this up. So we already established that we had this being the 2p orbital, and then what happens is that in blue, this is still part of the second This is still part of the second subshell. These cone-like looking subshells have one electron going up, the other electron going down, so that's 2. One electron going up, the other one going down, that's 4 electrons. And then finally in this last one, we have another one in fluorine. Okay, so if we count the number of those up and down arrows, you can see in the second shell we have 1, 2, 3, 4, 5, 6, 7 electrons, and that was consistent with our Bohr's model, right? So in Bohr's model we saw that we actually have 7 electrons. But Bohr's model is not as organized as this electron configuration that Schrodinger actually found. Okay, so the way we write this out in chemistry is we go, okay, in the second shell we have this S subshell to fill, so spherical, and we can only put in a maximum of 2 electrons. And then in this set, to get to fluorine from here, we need to fill in 4 more electrons. So that's called the second P subshell, and we have a maximum of 4 electrons to get up to fluorine. Okay, so actually that's 5, sorry. I was thinking it doesn't add up to 7. Okay, it's too early in the morning, I can't count. Okay, so we have the 5 electrons in the P shell, so 1, 2, 3, 4, 5. Okay, so this is actually the electron configuration for fluorine. It's this whole thing here. So as you can see and appreciate that is a lot more information, a lot more specific to kind of look at how electrons are arranged in an atom than is the Bohr's model. Okay, it just gives scientists a lot more information about the nature of the organization of electrons around the atom. Now, what you'll find is that the periodic table is actually broken down into these blocks, and they are specifically organized to tell you sort of which shells are, how the shells are organized, and in what orbital they exist. So you've got, as I showed you, the S block is the spherical. So this is the spherical organization. So you find that the there's the 1s, and that's in the first shell. You only have a maximum of 2 electrons that are possible to fill. So if you draw out hydrogen, you will just have a sphere around it, right? If that's the say the nucleus, then you only have a sphere around hydrogen, and because hydrogen is the very first element, it's only going to have 1 electron in that first 1s subshell. So this is the 1s. Okay, if you have something more complicated, you might have, you know, your nucleus here, you have the 1s subshell first, and then the 2s, which is a larger sphere around it, and then you have that 2p, which is going to be really complicated to draw. So it will come like kind of like this, that. It's actually a 3-dimensional thing, and this is a bit hard to draw, but that's the 2p orbital, sorry, subshell. So interestingly enough, there's a way of, it's important to understand that electrons won't just get filled in random order. They will always, within an atom, fill in at the lowest possible energy available to, so they will organize in a way where they will occupy the orbital that's at the lowest energy state first, and then it will kind of go out higher into higher and higher energy states. Okay, now we've got the S block, which are all the elements down from the first electron shell to the 7th. Then we have the P block, which we already looked at. The P block has the subshell is known as P subshell, and you can see that there are 6 electrons that are possible in the P block, so 6 electrons. In the S block, there's only 2 electrons. The D block, it's the transition metals. Looking at the transition metals, this has a maximum of 10 electrons. Okay, and the F block has a maximum of 14 electrons. I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, so 14 electrons can fill the F block. Okay, now we know how many electrons can fill in each subshell. Another thing to understand is I've talked about subshells. I want to make this clear, and I've also mentioned orbitals. Now subshells, the subshells are just the blocks. So there's a S block, there's a P block, there's a D block, and there's a F block. And these are basically geometrical organizations, and that occupy, that basically hold electrons. Now orbitals are actually, they're categories within a subshell, and an orbital is when 2 electrons only 2 electrons can fill an orbital. So only 2 electrons can fill an orbital. And I did mention before that an electron that points up must also point down. And this kind of collection of electrons, when one's pointing up and one's pointing down, once we have that's called an orbital. Now an orbital can only fit 2 electrons in it. So if you have a look at the S block, say there, the S block only has 1 orbital, because it only has a potential of 2 electrons, and one of these organizations, one of these boxes is considered an orbital, and an orbital has a maximum of 2 electrons in it. If you have a look at the P block has more orbitals. So that's 1 orbital there. This is another orbital here, because that's a maximum of 2 electrons, and this is a 3rd orbital here. Just show it in polka dots. Okay, so this is one orbital. So if I show this, an electron can point up and then can point down, and in the 2p orbital, an electron again can point up and one points down, and in the in this other orbital, another electron can point up and another one will point down, and that fills in these here. So one points up, the other one points down, one points up, the other one points down, one points up, the other one points down. Okay, so that was what I just showed you, the 2p subshells. and within that 2p subshells there are 3 orbitals, which is why there are, you know, this is the first orbital here, this is the second orbital right there, and this is the third orbital right here. So it's very complicated to consider these atoms in a 3-dimensional space, and I don't want you worrying too much about the geometry, but it is important to sort of be able to visualize it. So if you have a look at the D block, it's even more complicated, and this is where my artistic talents are not going to be able to draw a D block. Like, there's no way I'll be able to do that. But you can see that there are you just basically divide 10 by 2 and you'll know how many orbitals you have. So there are 5 orbitals in the D block. So there are 5 distinct places in the D block in geometric space where electrons will point up and down. Okay, and in the F block it's 7 orbitals. Okay, so I'll write that. Yep. Okay, so now let's have a look at something called the electron filling order. So this is pretty complicated, and I'm going to try to actually, I might do this in the next tutorial. For now, just try to get your head around that and watch the next tutorial for more information.